engineer of the team, coordinating the manufacturing of the car and a lot of the overall design. And then yeah, so that was my highest position on the team. Following that, I moved into being a design engineer at Edge Products. Edge Products, we do off-road buggies. Surprise, surprise. And that's one of our designs in the bottom right there, called a Barracuda. And so they're motorcycle engine-powered buggies. They do share a lot of common facets with the motorcycle engine Formula SAE cars and similar sort of vehicles. And that's my day job, designing those things, designing parts for them, analyzing them, all that kind of thing. In my spare time, I'm also a mechanic and navigator at Epic Racing. So that's the buggy we can see in the bottom left there. So navigating, I sit in the left seat and tell the driver where to turn and how fast to go. You can see my hand waving through the windscreen there, pointing him in the right direction, hopefully. So that's my experience with actual competitive racing there, outside of work. So. Okay, we'll go first step of vehicle design. I just want to make a note here that this is a seminar about the methodology, the process we use. I'm not going to give you exact values of this is precisely how much weight distribution you should have, because every vehicle is different. And what I'm trying to convey here is the overall process as we go, for example, in my job, as we go from a blank sheet, let's design a buggy, right through to having a complete CAD model ready to go manufacturing or testing, and then later on the finite element analysis and how we use that. So defining your suspension goals, and I want to start with probably the second point here of we design from the suspension inwards, and this is a really important point to make, especially with off-road buggies, but with motorsport in general. Obviously, how fast the thing goes, a lot comes down to, down to your suspension and how that works. And so you want to design the suspension first, generally starting with the wheel positions, as we can see there. And I want to make this point of let your suspension dictate your chassis. So we design the suspension first and then design the chassis to suit. When you let the suspension dictate the chassis will try and fight back. By that I mean the chassis will not be able to fit in certain places, but then you will only have to modify the chassis or your suspension where it really needs to be modified. If you design a chassis first and then try and follow it with suspension, your chassis is dictating the suspension. It's deciding what goes where. And sorry, we're just hearing some audio problems. Hopefully that can get cleared up. Okay, so if you design your chassis first and follow it with a suspension, your suspension is always going to be secondary. It's going to fit around the chassis, but it might not be the best that it could be. And I want to make this point at the bottom here. Design a good suspension and a chassis that just works, not a good chassis and suspension that just works. If you have good suspension and a chassis that just does its job of holding all the components together, that's a race car. That's a car that's meant to go fast because it's got great suspension. If you design a good chassis and then suspension that just keeps it off the ground, well, that's a truck or a family car. And that's a great process if you want a truck, but we don't. We want a race car. So we'll start with that overall point of we try and design the suspension first and then the chassis second. Okay, so first step there, we'll go back to the beginning here of defining our suspension goals. So we start off with some really basic parameters, and we set those at static ride height. So the height of the buggy when it's not being jumped or flying through the air or coming down off a jump or anything like that. Static ride height. What camber do we want? What sort of, say, for example, scrub radius on our steering? What ground clearance do we want? And there's lots more properties there which you can sort of examine in further detail. And then we look at travel. Okay, so we're at our static ride height. Is that halfway through our travel? Have we got 6 inches up and 6 inches down? Or are we looking at, sorry, we're just getting an odd technical problem here. Okay, we'll just keep going. Okay, do we want to go 6 inches up, 6 inches down? Do we want to go, Excuse me for a second. Sorry guys, we are just having a bit of a technical trouble at the moment. I'll try and get everything going again soon. Okay, so your hold on for a second, guys. Okay, sorry about that. Okay, where were we? All right, so we've got our static parameters. We're then looking at travel. How far through the travel do we want to sit? Do we want to sit near the top of the travel with a lot of droop but not much bump, or vice versa? And then we look at how things change with travel. And remember, what we're looking at here are pretty abstract numbers. These are numbers that sort of, they don't directly correspond perhaps to the vehicle itself, but we're going to use them later on to help lay out our vehicle. So things that change per travel as we go up and down through the travel. Do we want camber to change? Do we want caster to change? Usually the answer is yes. It's nice to have these varying in certain ways. Do we want our steering to change, i.e. bump steer? And that's a good example of something we don't want to change. And I want to make a bigger point out of this, that things not changing is just as important as designing things to change. Zero is a perfectly important engineering goal for something we don't want to change. All right, and then we can also look at things that change with our steering. As you steer the car, if your toe is changing, that's called Ackerman. A lot of you would probably be familiar with that. Okay, looks like our audio problem is getting better, so that's good. Okay, all right, so yeah, things that change per steering, for example, Ackerman, but there might be other things you would like to change. A pretty abstract example, if you have a, if you look this up later, but if you have a 5-link front suspension, then you can have scrub radius that changes per steering. That will affect your handling, but you might have to go look that one up. All right, so first step of vehicle design, these are our parameters we're after. We want to identify these numbers. From these numbers, we're going to hopefully build a race car. Okay, that's nice, but actually what numbers do we want? You know, we care what the camber is, but what's a good camber value? And this is where I can't give you a straight away exact answer. This is where, this is your design. Your vehicles are going to be different to what we use on our vehicles at work. So in my job, our vehicles are generally a lot larger, more powerful than Formula Baja ESI vehicles. So our values are a lot different. But where can you guys start? So physics calculations is a great place to start. Newton's laws. Look at weight transfer. You've got your height for your center of gravity. You've got your wheelbase and your track width, hopefully. What's that going to do for our weight transfer? You can do some pretty basic rudimentary physics calculations, which can give you a good insight into what sort of target values you should be aiming for. Should it be 40% of this, or 10 degrees of that, or 200 millimeters over here, or whatever these values are going to be. And other things like ride frequencies. Again, that's just basically your differential equations kind of stuff. Before you even get to any design process, layouts and diagrams, do some physics calculations. Second option is testing. Figuring out what your ideal parameters are from your older vehicles. If you can look at an older vehicle and say, well, this vehicle is great, except it always does this problem. Identify what's causing the problem, and that gives you a good starting point for your next vehicle. We'll talk about this a bit more in the next seminar, hopefully. Simulation, underutilized tool, simulation. Simulation can be very powerful. Even a very basic simulation can be surprisingly informative. It can give you a lot of information about what your vehicle might be doing. Now, every good simulation. So simulation was something I spent a lot of time on at university with the Formula student. The Formula SAE car. And some of those were just basic side view, front and rear suspension how is our braking gonna balance between front and rear, this kind of thing. Other ones is full top, yeah, what do you call it, a 2D simulation from the top down, and all of this was just written in MATLAB. It was raw simulation code. It did all the physics from straight lines of code. But any good simulation starts with a tire model. Now, I recommend you look up the Pesejka formula. I still don't quite know if I'm saying that right, but they're really good formula for modeling tires. They're quite complex because they come from tarmac racing, where tires are much more sensitive creatures, you could say, and they have a really big effect on vehicle handling. But the formula themselves and the idea behind them of modeling your tire response based on a few inputs, and then you can use that model as the basis for a simulation for the vehicle. And that simulation, yeah, can be in MATLAB or C if you want to write the code yourself. It has huge advantages. Or you can look at commercial simulation software, SolidWorks and ANSYS, and examples there that use rigid body motion. Very powerful stuff. Simulation also gives you sensitivity studies. And I want to make a point here. Excuse me for a second. Okay, cool. I want to make a point here. Sensitivity studies can be really powerful, and that's where you analyze something or simulate something. You don't necessarily get the exact answers of what's going to happen, but it can tell you whether something is important or not. It can tell you whether changing your brake bias is actually going to affect your braking distance, or how much is it going to affect it? Basically, how sensitive is it? And I want to give you something to look up later called ensemble forecasting. It's a really powerful tool. It's usually used in meteorology, but the core idea behind it can be really powerful for when you're simulating a system that has complex inputs and complex outputs. For example, a race car. And it helps you to identify things that are really important for your design, things that you really have to get right, and things that aren't so important that you've got a bit of leeway on. And finally, simulation validating against real testing data. If you have even just some basic tire data or performance data from your vehicle, compare it to your simulation, you can really improve the accuracy of your simulation. And from there, you have a more accurate simulation. You can get better ideas for what your suspension parameters should be. Remember, this is always coming back to what should my car's basic core numbers be? What ground clearance? What ride height? What camber? How far through the travel should I put it? And all these kind of numbers. That's how we can arrive at those. Okay, the importance of ranges or tolerances in your core parameters. So this is where you can arrive at some really perfect values. So I know my car's going to be the best if it has this number and this number and this number and all these great values. But the real world is probably going to get in the way of that. Somewhere along the line, you're not going to be able to achieve all of your ideal parameters. Of course, your ideal parameter is a really light car that has lots of suspension travel and is very stable and cheap to make. And already you've got contradictions there. So how do you choose? How do you choose what to prioritize? And I want to go down to this line at the bottom. Vehicles always have too many parameters and not enough information. If you've ever designed a vehicle, even one which is the Formula Baja ESI sort of car, it's relatively simple compared to a lot of vehicles out there. It's reasonably simple, but there's still lots of numbers there, lots of things you could change, and often you can change them in ways that you are hard to predict how they will affect the vehicle. There's not enough information there. I mean, if it was easy, everyone would be doing it, right? We wouldn't even be here. So too many parameters, not enough information. So which of these parameters are fixed and which are flexible? We see there. So you might have done lots of simulations and calculations, and you go, all right, camber 6 degrees. That's my best camber value, and I can prove it, and I can take it to the design judges and say, hey, 6 degrees. But it might not work out that way when you actually come to design the vehicle. Maybe it has to go 5 degrees or 7 degrees. Are they acceptable? How about plus or minus 2 degrees? Are we working between 4 and 8? Is that too much or too little? and having a good range for most of your core values is really important later on when it comes to to deciding who wins, who gets chopped, who has to compromise to make way for other things, um, and and how much of those compromises worth. So yeah, a really good idea too. Once you've got your core numbers, the numbers you want to have, figure out what you could live with in the real world. Okay, turning geometry numbers into actual real geometry. We can't just make a race car out of our core nice numbers. At some point, we actually have to design something, right? So there there are two overall avenues of attack for changing these raw geometry numbers, your camber, caster, bump and droop, and steering, articulation, and all that. Turning them into real geometry, real things like where are my pivot points, where are my shocks mounted, where is my rack and pinion for steering or bell crank, how long is my shock absorber stroke need to be, all these sorts of things. So turn this big jump from ideal numbers into real 3D geometry. The two main ways we can go about it. The first one is sort of via geometry programs, and I've seen this in some of the ESI design reports. So where we use a program and I put in my design data. Basically, I designed the car already, put the data in, and it tells me what my camber is going to be at 20 different travel points. So this is giving me really high resolution, but it's only one parameter at a time. So it tells me what my camber is going to be throughout the entire range of travel, every inch of the way. Or it might just tell me what my bump steer is going to be throughout the entire range of travel, or my shock absorber ratio. So we compare that to what's called holistic CAD geometry. So holistic means all together, all at once. We look at the whole vehicle. We don't just look at one thing. We consider the entire design all at the same time. Basically, this strategy is low resolution in the sense that we're only seeing our suspension travel at maybe 3 places, but it gives us many parameters at once, or sometimes all of the parameters at once. And really this means, what I mean by holistic CAD geometry is we set up a basic raw model of the car, we model the entire thing, right the way from the wheel face through to the chassis centerline. But it's only a very basic crude model. It's just enough to give us our core geometry. Remember our parameters of camber and caster and all those. Okay. And so these are sort of two opposing ways that we can design a vehicle like this. So why would we choose either of them in particular? Well, we look at tarmac racing. So our top picture here, one of our Adelaide Formula SAE cars. When you're racing on tarmac, it's a very sensitive environment. Half a degree here or there, 5 millimeters of travel makes a big difference. I've got very short travel. We might only have 50 millimeters of wheel travel at best. But throughout that wheel travel, I really care about what's going on. It's very sensitive. And so I want to know what's going on with my camber or my caster or my steering at every point throughout that travel. It's very important to me. Now, compare that to off-road. It's a much lower sensitivity environment. We can see that from our wonderful off-road buggy in the bottom picture here, who's doing a wonderful crossing over power slide. It's a low sensitivity environment, and that means that a degree or two here and there doesn't make a huge difference. A little bit of steering inaccuracy, maybe a bit of incorrect camber. We're not as worried. And we're also not as worried if somewhere between 40% travel and 45% travel, it's half a degree off from where it should be. That's not a big problem. So it's a low sensitivity environment. We've got broad parameters. Instead of our camber being between 2 and 2.5 degrees, our camber is between 2 and 6 degrees. It's much broader environment, and we've got a lot more travel to deal with. If we looked at off-road buggy travel, every millimeter of the way, we just have too much data to make sense of. So in off-road, we'll generally use a holistic CAD setup. And I'll go through now what that involves. Before we get to that, I want to make a bigger point about what I was just saying there regarding we don't care what values which are a bit more flexible. And this is a general principle for design engineering. It's something I hope everyone can take away to wherever you end up working. If you end up working in motorsport or in architecture or in submarines or aircraft or wherever you go, this is a general principle that applies to everyone. Knowing what is unimportant, that's an important thing to know. Like we said earlier, there are hundreds of things that you can measure on a car or you can decide. And if you try and optimize all of them, you're going to go around in circles and you're going to waste a lot of money, time and money as a commercial engineer. Remember that as you go through university, the eventual point is to work as a commercial engineer. Knowing that something is unimportant is still critical knowledge. So if you can come to competition and a judge says, okay, what have you done to design such and such a parameter, whether it's camber or caster or anything like that. Now you could say, oh, we spent lots of time and here's all our explanation of how we designed it and all this kind of thing. But sorry a second. How we designed it, yeah, that's great, sure. But at the same time, if you can turn around and you can say that aspect is not important, and here's our proof, so you must be able to prove it, show how and why whatever parameter it is unimportant, prove to the judge that it has a negligible or no effect on your car, and then that's a good engineering choice. That's a successful engineering investigation there. Showing that something is unimportant is just as critical as knowing how important your tow in on your vehicle, for example, is. And once you can show that something's unimportant, you can leverage that. You can throw it to the wind to advance something that is important. You know, don't spend weeks and months of what could be company time trying to make sure that I know that your acumen is absolutely spot on when for example, on a drag car. If you're designing a drag car and you spend weeks getting the acumen correct, it doesn't have any steering, or doesn't steer much. So you've just wasted a lot of time. Find out what's unimportant and be able to prove it. And that's sort of part of your job as an engineer, is to prioritize what are we spending time on. Time is money, etc., etc. So hopefully that's a message that people can take away beyond the field of motorsport. Okay, suspension architecture. So by this, what we mean is the overall type of the suspension: single arm, double A arm, one trailing arm, two trailing arms, a trailing three link. If anyone's familiar with the side-by-side type vehicles, with a tow link on a particular vehicle, five link, live axle, all your different options here. This is often obviously it's a big starting point for turning your suspension design into something real. It's hard to figure out a design if you don't even know what link is joining to what. But the question is, which one do you choose? Now, you could try designing and simulating all of them, see which one's better, but that's going to take a lot of work. So this is where it's important to be familiar with the different types of architecture, what their advantages are, what their disadvantages are, and how that affects your vehicle. Excuse me. And so one thing I can really recommend here is to go and explore what systems are being used in all fields of vehicles. Because if you just look at the suspension in one particular field, for example, off-road buggies, it might not be the best way of doing it, or you might not understand why it's a good way of doing it. For example, a suspension system might just be sticking around because that's the way everyone's done it. If you go and look at other fields of vehicles, okay, what are trucks using? Why are they using it? What are excavators using? Or earth moving equipment? What is a commercial car using that you go to pick up the shopping? What are other types of motorsport using? Formula One versus off-road racing versus rally. Why are they using it? And looking at the differences between these is really important to get that kind of gut feeling of, okay, a single A arm is good for this, but a double A arm is good for that, and being able to justify properly why you've chosen what you have. So, for examples of different ways that each of these architectures is a compromise between different properties, you have to compromise between the amount of travel you can get, its dive or squat properties, camber, caster, strength to weight, steering, how it attaches to the car. It's also very important. Ground clearance you can get, the chassis clearance. Do you need to cut away the chassis to make this thing work? Now, these are very basic properties that you can make a big table according to how each of these suspension systems works, the pros and cons, and that's all very well. But you also need to be able to look at what do these properties mean for the overall effect on the vehicle, and that's where we got our third column here. What about cornering speed? What about straight line stability? Can my suspension take jumps or impacts? Obviously, these properties are more relevant to off-road racing than, for example, a bus. But that's the matter of figuring out what's important for your vehicle. The aerodynamic priorities. If I'm running aerodynamic wings or that sort of thing, is my suspension going to react well to that? And finally, of course, manufacturing. Can I actually make my suspension? Is it going to be cost effective to make it? Do I need to have enormous billet aluminium components, which are really expensive? And various properties like that. So yeah, choosing your suspension architecture really has to be based on your own design priorities, the pros and cons of each one. So I can't really say much more on that without going into the individual vehicles. So okay, back to our holistic CAD. So this is a computer model where we're setting up the complete vehicle all in one go. Okay. All right. So 3D sketches are your best friends. So whichever CAD environment you're working in, hopefully you can establish a 3D sketch environment. And this is basically a 3D model, which is just your lines, nodes, dimensions, things that you can fix and things that you can leave unfixed. And this is our raw geometry. So it's just pivot points, arm lengths, your shock absorber lengths. So extended and retracted, where your steering rack is and how wide it is and how much it moves. We don't really care about any of the specific mounting widths or bolt diameters or anything too detailed like that. We're just looking at the raw body to body connections. Now, this is the real strength of holistic CAD is you sketch it at multiple travel points. So you have one model at full droop, one model at ride height, and one model at full bump. Maybe one's in the middle, but we'll leave those out for now. And also perhaps multiple steering points, so straight and then turned hard over, hard steering turn. And effectively your 3D sketching environment should be able to solve these simultaneously. So what you can do here is you can set up a full model. You can say, all right, I want to have no toe, so my wheels to be pointing forwards at full droop. At ride height, I want my shock to be compressed by 4 inches, and then at full bump, I want it to be compressed to 8 inches. And how much actual travel is that going to give me? Or I can decide, okay, I want this much travel, and then my model will solve where the shock has to be located in order to use the shock absorber stroke. And that's the huge advantage, is you're no longer designing a car hoping it'll work and then seeing if it works. You design it to work from the very beginning. There's a friend said there's no hoping involved. If you're hoping for something, you haven't designed it properly. Okay, so yeah, multiple travel and steering points, and they're updating simultaneously. You may need multiple sketches, but hopefully it should all cascade together and give you simultaneous updating. Now, conflicts will occur. Part of this is our compromises coming from the suspension architecture we were talking about. But you're going to get conflicts. Some types of suspension are just inherently have an inherent weakness. For example, a trailing 3-link will often give you a lot of toe change. And some of you guys might be familiar with that. I've seen plenty of trailing 3-links on the ESI cars. Now, that's not necessarily a bad thing. Well, it's a bad thing, but is it bad enough to do something else? And this is where our parameter tolerances come into it. We've laid out our CAD. We've had some conflicts going, okay, I wanted to have no toe in my suspension travel. My suspension architecture it's conflicted with that desire. It's given me 3 degrees of toe change on my rear suspension. Now I look at my parameter tolerance. Is that an okay variation? And this is where I need to stress that your parameter tolerances come in very handy. And you want to be deciding your tolerances before you design your car. If you design a car and then see if the tolerances are okay, then you're really just changing your design to suit the model, not the other way around. So this is where your parameter tolerances come into it. When you have to change one thing in order to try and change the other, for example, on AA arm front suspension, what do we want to do? We want to have more camber change to fit within our parameters. Okay, that's great, but that gives us more toe change because we can't get our rack position right. So which parameter do I compromise? Which parameter do I change to try and suit the other? And that's where our tolerances are really important. Now, the final point here is when you're doing all this nudging and modifying the design and shifting things around, you should start to develop what we could call layout sensitivity instinct. And that's a gut feeling of how the layout affects, how changing one part of the layout affects the others. So for example, there is that you might stand back and look at a design and go, okay, my rack and pinion is conflicting with something. I can see it's going to get in the way of my arm pivot. That can't work. They can't go through each other. So should I try and should I move my rack upwards to get it out of the way or forwards to get it out of the way? And your layout sensitivity instinct is that feeling, because you've been moving this model around maybe for a couple of days or a couple of weeks now, and you sort of got this gut feeling of whenever I change this, it has a huge effect on something else. And you'll be able, and that means you'll be able to solve these problems of, okay, it's conflicted, something's not happy with this. But I know that in the past, every time I move my rack up, I get a lot of bump steer, and it's difficult to get rid of. So if I move my rack forwards, I won't get as much bump steer. And that's a sort of shortcut to help you get around these conflicts. And we'll touch on that a bit more later. Anyway, that's so setting up your holistic CAD geometry. Okay, including hardware in raw CAD. So I don't mean actual hardware models of your shock absorbers, but we can't just build our CAD based on our ideal numbers of camber and caster and whatnot, because the car itself is going to be made from real hardware. So how do we actually include that in our lightweight lines and dots model? So first of all, which hardware do we need to include? Do I need to include in my raw model, do I need to include the bolt size that holds a seat on? No, because it doesn't really affect anything else. It's just wasted information. But for example, what we said earlier, my shock absorber stroke, that's going to be important. That's going to affect where my shock mounts. It's going to affect where my shock mounts to the arm or the upright or whatever. Excuse me. And other things like hub bearings. It might be nice to put my arm right in the middle of the wheel, but my hub bearings are not going to allow that. So I can build these hardware numbers into the model as geometry parameters. So we can have two sort of types of hardware there, and that can be your non-negotiable hardware. These are fixed values; they're never going to change. And that can be control components, so things that are fixed by the rules or fixed by your budget. So if your budget only allows you to use last year's rack and pinion, you don't have the budget to get a new one, that's okay. We'll design around last year's rack and pinion, but that's a fixed dimension, a fixed, fixed, say, width of the rack. We can move it, but we can't change how wide it is. And then we have proposed hardware. So this is where we do need the hardware to sort of join the dots and make it a realistic model, but it's not necessarily locked down. We've got example bearings that we're planning to use, but if need be, we can use bigger or smaller or make them further apart or anything like that. And your shock absorber lengths, it might be fixed for a certain shock absorber, but just bear in mind that you can change your shock. So in this way, your components, they become geometry parameters. And again, I don't want to see a model of a Fox shock absorber inside this raw CAD sketch. I just want to see, here's its open length, here's its closed length, and maybe one in the middle. And that's the kind of raw geometry we're talking about. And so, these geometry parameters can be reassessed or updated as the design is optimized, as you move things around, get a better idea of how it's going to be laid out and all that. Now, holistic CAD is also great in this sense because it highlights when a component is actually getting in the way of the design. So for example, is you say, all right, we're going to use this shock. It's got 20 inches here and 16 inches here. And now I'll design an arm to suit. But no matter how I design my arm, the shock is just not working. It always crosses to the other side of the buggy, or it always the sketch crashes because the shock doesn't have enough stroke, and it's just not working. Now, if I'd already chosen my shock, do I go, oh well, I can't design my suspension then? No, you change the shock absorber, and this holistic CAD shows you, it brings to the surface the problems that are really inhibiting your design. So no matter how I try and design this arm, I can't do it because my shock stroke is wrong. So I change the shock absorber, find a different one, and go with that. And again, this is where our layout sensitivity instinct comes into play. My gut feeling is that every time I move this arm, the shock absorber drastically changes. I want to move the arm a little bit, but the shock absorber is not letting me. So maybe if I change my shock absorber, it will give me the option to change the arm as I want. And obviously this applies to all parts of the car. I'm mainly talking about the front suspension, but if we look at the back, we've got a complex interaction between how the hub upright, whatever it is, how it moves, and our drive shafts. Do they get longer and shorter? How is their angle change? How far apart are our drive shafts mounted on the chassis, on the gearbox or the torque converter? For example, is that drive shaft angle, is that ruining everything? No matter how I try and change this, I want to get more suspension travel out of it. I just can't do it with that drive shaft angle. Does that mean I change my shock absorber? No. Or change my suspension architecture? Well, it's probably not going to help because my holistic CAD is showing me that the CV joint angle is what's causing the problem. So there's another strength of the holistic CAD and how that ties in with your layout sensitivity instinct. Okay, next ingredient, components. Now we do actually want to see real components. This is where we start either adding in components we have an existing model for example, your shock absorbers, or your wheels and tires and that sort of thing. And this is where we start modeling actual components, tube size, plates, joints, bolts and screws, all this kind of thing. And you can see we've actually gone a fair way through the design process before we do this. And this is where if we think back to that first comment of design is suspension first to go fast, and then design the chassis just to hold everything together. It just has to work. And similarly here, we design our geometry to go fast. We design our camber and our toe change and blah blah to go fast, and then we design the components to achieve those goals, to let that geometry do its work. Instead of designing components, designing an upright and an arm, and then hoping the geometry goes fast. Again, we don't do any hoping. We design it to go fast in the first place. Okay, so we're looking at chassis, arms, hubs, all this kind of thing. And again, things are going to go wrong. We'll get interference. We'll get our example from before with a tie rod might be in a great position to give us no bump steer. And that's wonderful. But then we try and design our chassis and there's a bar going right through the middle of it. Okay, what do we do here? Say we can't change the chassis, that bar is compulsory. So we have to move our rack and pinion. And again, that layout sensitivity instinct. Okay, my gut feeling is that I can move it forwards and backwards and I'll lose a bit of acumen, but I won't get too much bump steer. So that's my best avenue of attack instead of trying to move a rack and pinion up and down to get it out of the way of the chassis bar. So this process is by far the longest part of the design. You can get, with a bit of experience, you can get the first, everything we've done so far done reasonably quickly. If you've got good data to draw on and a good model and you know what you're looking for, you can set that up pretty quickly. That's pretty straightforward. This bit is where you keep running into problems. You have to backtrack. You have to redesign something. Sometimes you may find that it's just unsolvable. There's no way we can possibly get such and such to work. And you have to go a long way back, even to the point of going back to your holistic CAD and changing a AA arm to a 5-link and start again. And that's why this bit takes so long, is you've got to reassess all of these components. You may even have to contact suppliers and go, hey, this bearing, it's never going to work. Have you got one which is larger or smaller or stronger or all these kind of things? And as we go through here, we add in subsystems. We add in a fuel tank and any cooling, and then obviously your seat, and your driver accessories and all that. Checking all the rules and constraints, and again, it's just a lot of backtracking. But that's your general gist of that design, and that sort of seems like I know that seems a bit like waving a magic wand. Do this final step, and you'll have a race car. Really, this bit takes the longest, but there's not a huge amount more I can really say there. Okay, I'll just check through this, and we're looking pretty good. Okay, we'll move on to our second part of the seminar, which is FEA, Finite Element Analysis, and other numerical analyses. And by this, I really just mean we're not only looking at structural FEA, making sure things are strong enough. We're also looking at thermal. It was great to see some thermal analysis in the design reports. And the other types of analysis we can do with this. So we can do fluid flow, again, our simulation from earlier, and how we can actually use this in a design process. Okay, start with a bit of a negative. FEA is not a paintbrush that you just apply after a design is finished to show that you have a good design. FEA shouldn't be showing you that a design is good. FEA is an ongoing part of the design process. It's a tool. It's a tool to help you design something as the design is being well designed. It's just like Newton's laws. When you use these tools to help you design something from the ground up. And an example here is your hydraulic calculations for brake pressure, your pedal force, pedal ratio, master cylinder, all this kind of stuff. You wouldn't just pick hydraulic components and say the design is complete and then analyze it and see what your pressures are going to be and say, okay, that's great. It doesn't work like that. That doesn't make any sense. You use your hydraulic calculations from the beginning to design a good hydraulic system. Sorry, just 2 seconds here. Okay. Sorry, just had to check some technical aspects here. Okay, yeah, so we don't just use our hydraulic calculations to check that our brakes are well designed. We design them from the beginning using those calculations. And as an engineer, you should always be using FEA as a tool to help you design something. We're going to go through this in more detail shortly. But I just want to make a reasonably serious point here about your engineering decisions, and also involving FEA. FEA can be used to save or spend millions of dollars if you're working for a company and you FEA a component, and you find that you could use a lot less aluminium. You save your company millions of dollars, and that's fantastic. Or you might FEA something and you say, okay, we can't do this with a basic laser cut steel. We've got to use machined aluminium. It's a lot more expensive. We're going to spend millions of dollars on this. So you better hope that it's right. And at the point you never really want to be at, but you may well be, is it can be used in a court of law. So if something goes really wrong, your FEA it's part of your engineering design process. It's not just a toy you throw on the end. It's part of your process. And if it can be proven that you didn't FEA correctly and it led to a failure, which could lead to all sorts of horrible things, then it's taken very seriously in the eyes of the law, I suppose. So I just want a note there. Just always think of your FEA as a tool in your arsenal. It's a very, very helpful tool. It can solve some incredible problems, but it just needs to be used in that sort of matter. We'll go back to our diagram at the top here of people say FEA was successful, and they put that together as, well, we did it on FEA and it didn't break, and then we made it in real life and it also didn't break. Therefore, our FEA was successful, and that's simply not true. That hasn't told you anything. I could FEA a brick and it doesn't break, and then I make a house out of bricks and it also doesn't break. That FEA was not successful. It certainly wasn't helpful, and it also wasn't a good use of my time. So how can we use FEA? Let's do something constructive with it. FEA during a design. So we're going to look at two broad problems that FEA is really helpful when it comes to solving these problems in design. Our first one on this slide, complex components. So components that have lots of inputs, lots of outputs, and by that I mean there's lots of forces coming into them. They're attached in multiple ways. They might be attached in different ways, a ball joint and a weld. And there's lots of options for improvement. And a good example for this. Okay, yep, just check that. Cool. So a good example for this is the bulkhead we have shown here. This is a machined aluminium part. It's about 500 millimeters across, so it's quite large. And it basically held together the rear suspension from the Formula SAE car that I worked on at university. And as you might be able to see there, it's even got lots of steel brackets attached to it, which makes it very difficult to analyze. But we've got, I think, eight different inputs coming into this component. There's forces coming from lots of directions in different ways. And it's also attached to the chassis in 6 different locations. It's also got, there's a differential that bolts to it, which is also loading it up. So it's a very difficult component to just look at it by eye and say, okay, let's remove some material here. And this is the kind of component we're talking about for our first FEA usage. Complex components with lots coming in and out. They're hard to just eyeball, as it were. So how can we do something useful with this? I could just start with a big slab of aluminium. That'd be strong enough, but I know I can take some aluminium out. The question is, where can I take it out? And so our cycle we've got going on the right-hand side here, as we simulate the part, simulate the loading, get our results back, and we look for a cold spot. And by that I mean not necessarily a temperature cold, but a part which is, let's say, blue on FEA. It's a part that's not being loaded very heavily. It's not contributing much to the overall structure. And that's what I'm really trying to target with this type of FEA. I'm looking for areas that I can improve it. And I'm not necessarily looking for absolute values of 75 megapascals stress, or if we are looking at temperature, I don't necessarily want to know what the hottest part, what temperature it's getting to. I'm looking for areas that I can get rid of, that I can change, that I can remove material from, to make the design better. In a lot of cases, it's to reduce weight. Um, but that's the important point here is we're looking for efficiency, not necessarily the actual total values placed upon the part. So that's one example of where we can use FEA during the design process. And our second other type of example where we can use it, we've got here. So this is for simple components. So instead of an enormously complex bulkhead with 10 things pushing on it and 6 things holding it in place, we're looking at something very simple. So for example, it might be a conrod in an engine. It's pretty simple. It's got a bearing at either end and it pushes and pulls in the middle. Um, and I can eyeball that. I can look at that and go, yeah, we could remove material from the center section, make an I-beam out of it, and then I could probably keep making that I-beam thinner, and it would save weight. And that's probably the best place to save weight. And I can see that with the naked eye, but I don't know how much I can take out, and it's difficult to analyze this by hand. I can't really do hand calculations because of the curves involved. But I'm trying to target one particular part of the design and I'm trying to fine tune that. And now I am actually looking for a specific numerical outcome. So it might be a factor of safety. I want it to be 2 times stronger or 4 times stronger or whatever we choose. Or it might be an actual value. Like I want to make sure this component doesn't get above 80 degrees Celsius or whatever. And so our cycle now is, once again, we simulate the load on the part. We're now looking for actual numbers. We're calculating our factor of safety, whatever that value may be. And then we're modifying the part until we fine tune that factor of safety. So I analyze it. I don't want it to exceed 80 megapascals. I can see that the area I'm looking at is at 90 megapascals. So now I can remove a certain amount of material from the design, reanalyze it. Now what's the stress on it? And so this is quite different to our first aspect. Our first type of FEA, where we didn't really care what the actual numbers were. We're looking for the bits that are that we can remove without failing the design. Now I'm actually looking for how much exactly can I take out. Examples would be an I-beam, wall thickness of a hollow axle. Okay, I know that I can just make it hollower. I don't need a computer to tell me, hey, take material out of the middle. But I want a computer to tell me how much material I can take out of the middle. Wheel spoke width, if you're making your own wheels. Gusset size, again, it's an obvious design scale, but where do I sit on that scale? And so this is sort of the two broad areas of attack for using FEA during a design. Using it as a tool, just like we would any other engineering tool, to try and make our design better. And hopefully we can really see teams focusing on these two areas and being able to justify to the judges, we FEA'd this component, it let us develop our design, it let us remove material from here, here, and here, or it let us trim back the component until it was exactly as strong as it needed to be. Okay, but there's an exception. Of course, there was going to be a but. So the exception for FEA is the rare case of analyzing something after a design. And for this presentation, I'm just going to look at vehicle design. Obviously, we can branch off into forensic engineering, where something is already broken, and then we FEA to see what went wrong. Obviously, that's hopefully a separate field that you're not investigating with your race car. Hopefully it doesn't break. Okay, but within motorsport, very rare cases where we want to analyze something after it's been designed because it is entirely governed by outside conditions. I look at a component and I go, okay, I have no input on this. It is doing the exact job it has to do. It bolts to this and it bolts to that, and it has to be made from plastic and it has to be 10 millimeters thick. There's nothing I can optimize. Is it going to break? Can I actually use this on my car, or do I have to throw the whole thing out and change to a different system? My first question: are you sure? Are you really certain that there's nothing you can optimize on this part? If there is something you can optimize, that's fantastic. Let's go back to our previous two options. If it's complicated, do number one. If it's simple, do number two, and away you go. Are you sure you can't do either of those? So if another team comes to competition with the same component as yours, except it's better, then you were wrong, and you should have looked more closely, and you could have optimized it. So actually double check. Are you sure? Number two, before we FEA it, can we do physical testing? Physical testing isn't just something for primitives who don't have access to modern computers. Physical testing is still really important. Um, it's it's underrated in how informative it can be. Um, and this can either be proof testing, so we just stretch it to the point where we want it to go. We see how much it elongates. That's fine. We let it go and everyone's happy. Or destructive testing, where we keep stretching something until it snaps or it bends or it buckles or it melts if you're doing temperature testing. And all these sorts of things. And now these can really give you a lot more insight than FEA. FEA seems great because you get lots of colorful plots. You go, oh, here's the stress and here's where it's, all this kind of thing. But it only gives you information as far as its own internal rules. There are rules within the FEA equation, um, and it's only going to give you data which complies with those rules. And if your design started to move outside the rules, then it's giving you the wrong data. So if you can't if you can't optimize a component, but you just want to know, is it going to break or not? Before we get to FEA, try physical destructive testing. If it's that simple of a component, hopefully you should actually just be able to do some destructive testing. It doesn't need to be really sophisticated NASA test laboratory. You can get away with reasonably simple tests as long as they're safe. But it needs to, you can learn a lot more things, how it fractures, how it elongates, how it fatigues, how it buckles, where it buckles. If you're doing temperature testing, we can look at, often temperature is very, I want to say unpredictable. Obviously, the point of FEA is to predict something, but the way temperature moves can still be even difficult for FEA to get an accurate grip on it. So if you're doing temperature testing for something, try doing it in real life, see what happens. You can learn a lot from it. It's often more accurate than FEA. And again, that comes back to FEA really is a simulation at best. And sometimes it's the simulation we'd want to do in FEA is limited by, like I said, the internal rules of the program. So yeah, physical testing is a great option. If that's not an option, for example, a complex, expensive component like a chassis, and now we can go to our diagram on the right here. This is a analysis of a chassis idea impacting sideways onto a round post. And obviously, this is not something we would hopefully encounter. We don't race near posts or trees. It's an example simulation of proof of technique. But obviously we don't want to build a chassis and then go smashing it into walls or wrapping it around trees. It's very expensive. It's potentially dangerous to test these things. Obviously, you're not driving the car, but there's still complex and expensive things to set up. So we actually don't want to do physical testing. So we get to number 3. FEA is actually the only option. What do we do? And this is where we need to look at what would you do if you could physically test it. If money was open and you could have as much testing facility as you wanted, what would you do to this thing? Rather than just approach it as I've seen this in some of the ESI design reports, the chassis analysis is sometimes it's a specific set of loads applied to the chassis. In real life, okay, if you did have a spare chassis, if you suddenly make a spare chassis for free, what would you do to it to test it? What would you want to learn from it to see if it's strong enough or not? Would you put it on the floor and apply 2,500 newtons to the roof bars? No. If you could do whatever you wanted, you'd drop it off a cliff. You do something much more creative. So if you really do have to just FEA it, be creative. You can do some pretty elaborate things in simulations. And the best thing here is you're only doing it once. I say you're only doing it once, except for things like mesh convergence or uh, error validation, this kind of thing. But in general, you're only doing this run a single time. So be creative. Use it to try and simulate your actual real world situation. Get that information that you want. Um, don't do a cheap, boring simulation when you could have just done a cheap, boring test in real life. And so look into things like dynamic plasticity. This is what we're seeing in the simulation on the right here. The chassis has started wrapping around the tree. Excuse me for just a second. Of course, it wants to update in the middle of a presentation. Okay. Yeah, so dynamic plasticity, this is where the chassis has started to bend and started to wrap around things. And this is obviously very expensive to test in real life, but it's something that the FEA can do in a relatively accurate sense, and it can teach us a lot. So do something you're actually interested in. And a lot of this comes down to going and doing the research. This type of FEA we've got sitting here is a thing called explicit dynamics. And that's what they often use for crash testing cars into walls or barriers. And that sort of thing. Is really interesting field, and it does some pretty cool stuff. Look at transient heat transfer. If you only have to simulate something once, go to town. Make it a complex simulation that takes half a day to run. Doesn't really matter how long it takes to run because you're only doing it once. So make it something interesting. If you simulate something and go, we had to FEA it because we couldn't do physical testing and we couldn't use it in our design process, because it was out of our hands, and therefore we only tested it with one force on it. So, well, that's a waste, and it doesn't tell you much. If one force applied to it was a useful design situation, then you really could have just analyzed it in the first place. So yeah, that's that exception for FEA. Okay, FEA boundary conditions. Just excuse me for a second. Okay, cool. FEA boundary conditions. I wanted to compare these two statements. Number one, I don't know what FEA boundary conditions to use, is equivalent to saying, I don't know what the component is doing or how it does it. Essentially, your FEA is getting the component to do what it should be doing. And that may sound kind of cryptic, but really, I'm not FEAing the component to see if it performs well under some abstract condition. I want to know if it's going to break or where I can fine tune it for option one under real world conditions. So my boundary conditions should always try and recreate the real world as much as possible. And a good place to start there is real world testing scenarios. Again, we'll go back to that strategy. If I could test this in real life, what would I do? I would support it here, I'd support it here, and I'd put a big weight in the middle. So do that in FEA and try and do it in a way which recreates your real world scenario as much. Okay, so, and a good way of checking this, have I actually done this in a realistic manner, is to look at your support reactions. So in this particularly obviously applies to structural analysis, but hopefully it expands to things like thermal as well. If I'm doing a structural analysis and I support my component at one end and support it at the other end and push in the middle, I would expect my reaction forces at either end, and any good CAD program will tell you what those forces were during the analysis. I'd expect them to be realistic as well. And a good example there is when you simulate something that is supported by a spherical ball pivot at one end, and we run the analysis, and then we come back saying, oh, there was a torque reaction at that support. Well, there should not have been a torque reaction there. It's a spherical pivot. So something's gone wrong. Part of our setup is incorrect. Okay, yeah. So yeah, make sure that your support reactions are accurate. And the other one to look up there is remote load conditions. I won't go into that for now because we're running out of time. But yeah, your remote load conditions, really handy tool. So just probably the most common mistake with boundary conditions, I'll just touch on, is unrealistic fixation. For example, our spherical pivot, which is fixed in rotation. Unrealistic fixation can give you a dangerous underestimation of your stress. For example, we simulate a component where it's fixed at either end. We put a load in the middle and everything's fine. But really, in real life, one end of my component is going to start to rotate and then fail. And our FEA didn't pick it up. We designed the component, put it on the car, and then go loading it, and it rotates and fails. So that's where our FEA wasn't correctly fixed, and therefore led to led to the wrong data. And so flexible neighbor components. And so a good way of making sure that your boundary conditions are much more accurate is you simulate the components that support the component you're examining. So we've got a big, say, aluminium component in the middle. It bolts the three other things. And so I actually simulate those three components as well. If they're all relatively simple, then it shouldn't add too much to your mesh. Bearing in mind, I don't really care too much about the exact details of the stress within those components. They're just there to offer flexible support. So for example for that is that big aluminium bulkhead we saw earlier. Where it attaches to the car, it attaches at 6 locations. Now, if I just fix them, it's not accurate because where the space frame chassis attaches is flexible. The space frame twists and distorts, and it can bend either way. So I need to be more accurate of how I define the fixing points for my analysis. So an option there is to simulate the bulkhead and also the rear third of the chassis. And then the chassis can deflect in a more realistic manner, and then it supports my bulkhead in a more realistic manner and gives me a more accurate analysis. Alrighty, and basically final one here of an engineer's decision to conduct FEA. And this is expanding the idea more to commercial engineering. When you're an engineer working in the real world, excuse me just a second. Yep. When you're an engineer working in the real world, FEA takes time and money. It's a costly process. And you always have to be asking yourself, does the cost of the FEA that I'm doing, how does it compare to the benefits? Am I getting my money's worth? And is my company getting its money's worth? Does this FEA save the company money? For example, less material would be needed, less machining, or can we get rid of parts? Does it save the company time? I might do an analysis and it shows that all those extra weight saving holes don't really contribute anything. So we don't drill the holes, we save company time. Fantastic. Or does the FEA earn the company money? Is there a way to make the component stronger and therefore a better performing product, or the product might be faster or lighter or cheaper, and we end up making more money out of it? So you need to, when you eventually graduate and go off to be commercial engineers, you always need to keep this in mind. And this is a great thing about playing with FEA as a student in Formula SAE or BAHA or ESI, is that you're in a prototyping environment. You don't have as much of that commercial pressure. So I really encourage everyone to use this time to explore FEA as much as you can. As a student, don't just treat it as a tick the box. Yes, I have used FEA, pass, next. Really explore it. Find out what its weaknesses are. Find out what it likes and what it doesn't like. Because the knowledge you gather in this environment where you're not on company time, you can make these mistakes. You can spend time analyzing something and go, well, that wasn't very helpful. Now I know not to do it in future. The knowledge you gather doing this as a student makes you a much better engineer when you are on company time and you're in time critical jobs. You might find another graduate engineer next to you is going, yeah, let's FEA this. It's that's definitely something we can do. And you can go, no, I've got the experience. I know that we're going to waste time if we analyze this with FEA. It's not going to gain us anything, and you've just saved company time, and you've really fulfilled that job as a design engineer. And a big sort of takeaway there when it comes to FEA is that customers don't purchase based on an FEA picture. No one walks into a shop and says, I want to buy that off-road buggy because it's got a great FEA plot. It doesn't happen. People buy things based on the cost, or how much it weighs, or how much time it's going to take for you to design it. So don't try and treat your FEA like it's a sale point. Treat it like a tool. I don't try and sell a brake system based on the equations behind it. I sell it on the fact that it does really good braking and it's cheap and lightweight. So don't try and use your FEA as a sale point for your vehicles. Use your FEA to give you a cheap, light, quick, fast vehicle, because that's what's going to sell. As an engineer, that's your job, is to make choices like that which are going to sell, not necessarily to make FEA plots that look great, because your customer really isn't that interested. Okay, next webinar. So that's the end of this one. Next one, we'll be looking at field work. So we'll move away from our design space, get the buggy built, get it out there, make some noise. But when we go field testing, what do we do? Do we just drive around in circles? How can we instrument the vehicle? What do we want to measure? What are some good test scenarios? What are your general field testing procedures? What are you looking for? What are you looking out for? What kind of feedback are you looking for in the vehicle? Do you want to know if it's got a nice color, paint job? No, we want to know how fast it goes, and we want to know why it does it. And identifying vehicle faults. And then we'll also tie this in with validating your design procedures. And yeah, so your testing can make effective use of testing time, and that's for both drivers and vehicles. For example, we've got a plot here from some field testing we did a couple of years ago, where we're comparing a simulation run in the red with the 3 blue lines, which are vertical acceleration over a jump. So yeah, interesting stuff. Okay, we'll just check in with our organizers here. And while we're getting that sorted, I did receive questions from students who posted them when they were signing up for the seminar. So I'll just start ticking through some of that stuff. There are a few questions which overlapped. So if I don't answer your question directly, I've probably tried to blend it in with some of the other questions just to try and cover some more points. So for example, sorry, just a second. Just 2 seconds as we sort this out. Okay. Yeah, okay, so we'll go into, yeah, so the questions that were posted when you signed up. Okay, so some of our questions are about track width. So obviously the distance between your front wheels and the distance between your rear wheels and your wheelbase, how far apart the front and rear wheels are. So you can sort of think of this as our vehicle footprint. And people are asking, what's a good ratio? How do you decide this? How do you decide how big the thing is? Again, as with the whole presentation, I can't really give precise answers. It must be so many meters. But I can sort of list off some priorities. So some of your first priorities are the hard limits on these numbers, which is going to go into maneuvering. If your vehicle has to fit through a certain size gap, it has to fit around a certain size corner, then that's obviously a hard limit. There's no point designing a vehicle that can't do that. So that sort of probably sets your upper limits for some things. Vehicle transport, you've got to move this thing around. You've got to fit it on a trailer or a truck. You might have to fit it into a certain storage area. Moving into the commercial sense, you might have to freight these vehicles all over the world. For example, at Edge Products, we ship vehicles all over the world, and part of our design does come into, okay, how can we ship this vehicle in a cost-effective manner? So yeah, so that can sort of help lay out your limits for the vehicle footprint. Second priority is looking at the vehicle's stability in terms of is it going to slide through a corner? What's the risk of it tipping? I know there is a bit of rubber side upwards action in ESI, but obviously that's not ideal. You're not going fast as a race car when you're upside down. So what are our minimum dimensions set by our center of gravity and by our tire coefficients? And again, that sort of comes back to those really early on, those basic physics equations of given such a tire coefficient and I want a corner at this speed, how big can my wheelbase be? In terms of the ratio between your track width and your wheelbase length, this comes to our third priority of what I might call dynamic stability. And this is where the ratio comes into it of you call it your straight line holding stability. So if you're at top speed flying along in a straight line, is the vehicle twitchy? Is the driver fighting to keep it in a straight line? Could the driver take his hands off the wheel and the car would just keep driving in a straight line? Or is it going to go veering off at an angle? And so obviously having a longer, narrower vehicle is going to be more stable. A shorter, wider vehicle is going to be less stable. And stability isn't always a good thing. Well, too much stability is a bad thing because you also want, sorry, just 1 second. Just hold with us for a tick. Okay, yeah, so we've got some other questions. I'll just quickly spin through the ones we've got here. And then we'll get to some of those. Yeah, so your straight line stability for your vehicle, but you want it to be unstable in the sense that it does actually turn into corners. It needs to do that sometimes. I can't really give you a solid ratio answer on that, but hopefully those sort of properties can help you out. And this is where your simulation, I keep coming back to it, simulation is fantastic because once you put the time into setting up your simulation, you can test all sorts of different ratios, and you haven't spent $1 on any steel, and you can try 20 different vehicles, all with different track to wheelbase ratios, and yeah, sorry. And see which one has the best stability, which one has the best turn in, which one gives you the best compromise. So hopefully that sort of helps on that point. One final thing, obviously your pitching and rolling moments given given what sort of bumps you have to drive over. Obviously a pitching moment, if you go over a jump, how stable is the vehicle from pitching nose up, nose down? And then your rolling moment is if one wheel hits a bump, gets kicked upwards, how much is that going to try and roll the vehicle off to one side? Is the vehicle just going to accept it and keep going? And again, there's no exact answer on that. You can go, if it's too skinny, then it's going to roll straight over. If it's too wide, then you've wasted, say, maneuverability or wasted steel and weight. But hopefully there's sort of some general ideas that can get you going there. Roll cage design. How connecting the roll cage in with the suspension. Obviously, we touched on that earlier, saying design the suspension first, then design the roll cage to suit. Try to compromise the roll cage design. Obviously, make it strong enough, but compromise it in the sense of deviate away from your ideal sense to suit the suspension and not the other way around. And always keep in mind that your chassis is really just there to hold everything else together. Your chassis doesn't do any particular job. It just keeps everything else working to do their jobs. To that extent, okay, we say, yeah, the chassis has to house the driver. Well, true, but the we're trying to say about this. The chassis just needs to leave room for the driver. The chassis interacts with the driver in the way of the seat and the harness mounts and maybe a headrest, but designing the chassis designing the chassis bars with a driver in mind uh, can lead you to some poor designs because the chassis' only interaction with the driver is to not get in the way. That's all it has to do. Now, within the chassis itself, we've got some great design ideas like triangulation, watching out for zero force members, except for buckling control. Efficient use of bars, so hopefully having each chassis bar does multiple jobs. That's always great. But a lot of those are just sort of general, I guess, structural design rules. And finally, looking at the commercial aspect, and hopefully within your ESI vehicle designs, where you're considering um, that uh, ideally the vehicle might be built by a company. They might build 1,000 or 2,000, and so is it going to be commercially viable? Should my chassis have lots of bends in it? Should it have lots of laser cutting? Is it going to be easy to jig? Is it going to be easy to actually build the thing in a factory? Now, within ESI, you're probably just building one of these things, but hopefully at least keep it in mind. And when it comes to design judging, sell the idea to the judges that you've thought about your chassis being an easy to design, because it probably is the most complicated part of the vehicle, and it's a place where you can win or lose a lot when it comes to making it a commercially viable vehicle. We'll also look at here. So another question was on the trade-off between acceleration and top speed. So obviously this is a bit of a gearing question. What sort of gearing should we use? What should our CVT, if you're using a belt CVT, how should that be set up with stall and maximum and all this kind of thing? Really, this is it's a good question to start with. Ultimately, it boils down to how long your straights are and how fast your corners are. But the point I want to make here is that when you're weighing up between two opposite or two opposing properties, do we gear fast for top speed but poor acceleration, or do we gear slowly for great acceleration and poor top speed? This is where you want to be looking at your lap. Try and record a lap, whether it's just on video, but hopefully you're recording speed, position, the length of the straights. And look at during that lap, how much were you at top speed? How much were you speed limited by your vehicle? How much were you just accelerating? You wish you could accelerate more because you never reached top speed. So maybe you could have favored acceleration some more. And this sort of ties in a bit more if you want to be more sophisticated with a lap simulation. And that's just a simulation of straight corner, straight corner, straight corner, away you go. And again, that can tell you a lot about the strengths and weaknesses of your car. Set up your car model in the simulation to have lots of different sorry, where was I going? Lots of different acceleration and speed balances, and see which one wins, see which one is a faster simulation, and that'll hopefully give you some ideas there. Okay. Yeah, and look at how much each increase is actually respectively better for your car. If you can increase your top speed by 5%, but increase your cornering speed by 5%, which one is actually going to make your car faster? Do you spend more time at top speed or more time in corners? And so this kind of breaking it down to a numerical sort of weighing up one number against the other is hopefully good to to try and get a bit more of an engineering aspect to your design rather than just piecing something together. And we'll also look at here, design validation. So sort of two types of validation we can do here. Hopefully this is a matter of you've designed a car, you've designed it with some engineering thought behind it, and now we've built it, but how do we know that we designed it correctly, or how do we know that it's actually being built to behave the way the design meant to? So you can do some basic ones, like your suspension tests, lift it up and drop it, or lift one end up and drop that. It's a bit safer. And from this you can measure displacement, frequency, your damping rates. You can get a lot of useful information out of it. Compare this to your simulation or your physics calculations, See if you're correct. See if you need to add some correcting factors and that sort of thing. Weight transfer during cornering or during acceleration and braking. Again, you can do some basic field validation. We'll cover this a bit more in the next seminar. But your high level validation, again, sort of comes back to or driving laps if you can get a test track. And for example, seeing if say, okay, we chose a brake bias of such and such to give the best braking because we thought from our simulations or our calculations it would give our best braking. So go and try it, but don't just try the one you've got. Try different bias ratios and see if they're better, see if they're worse. How much worse are they? Was your original calculation good? So that's some ideas for validation of that sort of thing. Okay, now we'll just jump over. Okay, I'm just going to go through a bit of stuff. Excuse me for a second. Okay, it seems like our organisers are doing a great job with the questions. I'm going to address one of the ones regarding the Pesejka formulas and how significant they are for describing your tyres. Obviously, your tyres are important. Your tyres do all of the interaction between your car and the world around it. So they're obviously very important. The Pesejka formulas, named after Mr. Pesejka, they're a group of tyre formulas where basically you put in what the tyre's slip angle is, what its slip ratio is, how much weight's on it, and a few other, its camber angle, a few other properties, basically how the tire is interacting with the ground right now, and the formulas put out the forces you're getting. Those forces then apply to your car. Well, they apply to your suspension and then applies to your car. And from there, we figure out how the car's behaving. Are the Pesejka formulas really that important in describing a tire? On tarmac, yeah, absolutely. They're fantastic. And they... if you look into the Pesejka formulas and you can see why in the original paper, I think from 1984, he describes what he's trying to achieve, what's wrong with the existing models, and that's an extremely insightful description there. You don't necessarily need, you certainly don't need to be as in depth as his stuff. The real detail in those formulas and the way they've progressed over years since is great for tarmac cars and for really high level tarmac motorsport, Formula One, where they need to get the absolute last 0.5% of performance. Like I said, in off-road, your parameters are a bit more broad, and you can be a bit more flexible. So you can get away with a much simpler tire model. You can sort of come up with one of your own. If you maybe start with some of Pesejka's real first basic formulas, which only maybe have 5 coefficients. So that's 5 numbers which describe the tire. You can get 80% accuracy, maybe higher. All the extra formulas all the extra coefficients in the more advanced versions are really just for the extra detail. And for the most part, off-road, like I said, it's more variable. It is harder to predict. Simpler vehicles, and we're really just looking for general trends. So you can get away with a really rudimentary tire model. Really just have as long as it gives you the basic curve shape that you can see in those diagrams, and as long as your 4 or 5 parameters give you your maximum grip, your initial slope, how quickly it drops off, and where it drops off to, that's a really great model, and that'll give you a lot of insight on that. So it's something you can then play with later on. And once you've come up with that model, run a few simulations, change the model, see if it changes the simulation, and that'll give you an idea of whether it's actually important or not to have a more elaborate model. So hopefully I've answered that one a bit, but I do recommend looking up tire models and off-road tire models as well, because it does vary a bit. Okay. All right, so another question has come through on YouTube. What do I mean by layout sensitivity instinct? I'll try and just spin back through the slideshow to where that came up. All right, layout sensitivity instinct down the bottom there. So what I mean by this is it's the gut feeling of when I change something in the layout, what effect does it have on the things around it? So once you've done one of these holistic CAD everything up at once, well, not everything, CAD up your raw geometry at once. Once you've done that, it often looks like a big pile of lines. It's hard to tell what's going on sometimes. But you'll find that the things you've fixed obviously won't change. And as you change other parameters, things will shift by themselves. So for an example of that is I set my shock absorber stroke, and I set how much my wheel travel is going to be, and then it has to figure out, it has to put the shock absorber at some point along the suspension arm to give me the correct response. The layout of the sketch forces it to do that. If I then change my shock absorber stroke without changing the wheel travel, it's got to move something else. Something's got to shift to accommodate the change I've forced upon it, and so it will move the mounting point along the suspension arm to suit. Now, after you've played with a model like that for a while, trying to achieve different things, you'll get an instinct, a gut feeling of, if I change this, it'll affect that. If I change this, it won't affect that. It won't have any influence on another property, but it will impact this other property over here, and it'll have a severe impact on that. And so I gave an example earlier with a rack and pinion and how you move that in different directions, and you get a gut feeling of which directions are okay to move in because they don't affect other things, and which directions have a big effect. Another version of that is, say, when you're moving if your shock absorbers are, you've got a double A arm front suspension, your shock absorbers lean in towards the center of the car somewhat. Now, moving the shock mounting point on the chassis, moving it forwards and backwards sort of swings the shock absorber slightly forwards and backwards, but it doesn't have a huge effect on the motion of the wheel. Now, you could have figured that out from 3D Pythagoras and doing geometry calculations and all that, but the CAD model will tell you that straight away without you having to do those calculations. But if I try and move that shock absorber mount towards the center of the car or outwards away from the center of the car, it will have a huge effect on my wheel travel. And that basic knowledge of, or that gut feeling of forwards backwards makes no difference, side to side makes a huge difference. The more you build up that instinct, that sense, how the layout is sensitive, i.e. your layout sensitivity instinct, that knowledge comes in handy later on when suddenly you go to design a chassis and there's something in the way. You can't put your shock there. It's never going to be able to mount to that location. You go, okay, do I move it forwards and backwards, or do I move it side to side? And without having to test both of these options and try and solve the problem manually, you've already got that gut feeling. You already got that instinct that if I move it outwards away from the chassis, it's going to mess with all my wheel geometry and I'm going to have to recalculate all that. If I just move it forwards 50 millimeters, it won't have as big an effect. And so it's sort of a shortcut. This instinct is a shortcut to solving that problem. So I hope that sort of answered the question about what layout sensitivity instinct means. I'll just check in now. Check in now and see how we're going with our organizers. We've been going for over an hour and a half now, so I hope everyone's still with us. Yeah, okay. So that'll basically conclude this webinar. I hope I've answered people's questions. if you get in touch with the organizer of the seminar, the Enduro Student India organizers. I'm happy to answer any other questions after the seminar's over. If you can get in touch with me. Again, I'd stress that specific engineering questions of should I use a M8 bolt or an M6 bolt? These are probably questions that uh, best you try and try and answer them yourself. In the sense that you, as an engineering student, you probably already have the tools to answer these questions. It might not be obvious, but you've probably either you or your teammates or maybe your lecturers. You can always approach them. Hopefully, we'll have the tools to answer these questions. Hopefully, what I've been able to contribute is the methodology of what broad steps do we take to try and design a fast vehicle and design it in an efficient manner, not just designing it blind in the dark, but hopefully a directed design to try and get you to a fast vehicle with a